This video deals with three phases in soil and how we use it to describe soil samples and soil constituents. When we collect samples in the field, we would like to know its consistency and its properties. We will examine it very carefully, and we will notice that each soil sample consists of soil grains or soil particles, which will make the matrix, and there will be a space in between those particles, what we call voids. Like we have see, this is void, this is void. These voids can be filled with water, or they can be just empty or filled with air. If we look at this schematic diagram, we will see that S stands for solids, and these soil particles, and between these soil particles we will see voids, and these voids can be filled with water. This blue material, it's water, or it can be also filled with air bubbles, which I highlighted in green. We need to consider these three phases, and using these three phases we will see how we can describe the soil properties. What I would like to do next is I would look at soil sample, the one that we collect from the field, and I will just represent it using this phase diagram. I will simplify it. I'm going to look at the amount of solids and the amount of water and also air. What we will do next, we will look at the amount of each component. So we're going to look at the volume of solids, at the volume of voids, and we will use these two parameters to describe soil properties. On the other hand, we can also look at the soil mass, and in particular we will look at mass of solids and mass of water, because air has no mass, no weight. What we will do next, we will describe soil properties based on either the volume of each phase, and this is what we're going to call volumetric ratios. The most important of volumetric ratios are void ratio or porosity and degree of saturation. And we will do the same thing, but we will use the mass of each component. And this is what we call the mass ratios. The most important density and water content. Void ratio indicates the amount of voids in soil. Basically, it answers the question if the soil is loose or dense. The formula for the void ratio is shown here. We need to know the volume of voids, so this one, and we will divide it by the volume of solids. If we have lots of voids, then this void ratio will be very high, which means that the soil is loose. If we don't have lots of voids in the soil, in this case the void ratio will be relatively small, which means that the soil is dense. Void ratio depends on the type of soil. For most of sandy material, it may vary from 0.6 to 1. For clay, the void ratio typically is much higher, so it can be as low as 0.8, and it can go to high values of about 2. For some organic soils, the void ratio can be as high as 5. What does it mean? It means that this soil will be very, very loose, And this means that the soil is not a very good foundation for structures. Sand, because it has a low void ratio, is a typically better foundation than clay or even organic soils. Another thing that I would like you to remember is that when we present values of void ratio, we just use it as ratio. We don't change it to percentage, so this will be incorrect. Porosity, it's not very common for soil, but we use porosity sometimes, and porosity is very common for rocks because rocks don't have much void space. So for you to know that porosity is the ratio between volume of voids to the total volume of the sample. So this is going to be volume of voids divided by the total volume of the sample. And void ratio and porosity are related through this equation. It would be nice if you can remember this one. Degree of saturation indicates how much water is in the voids. It is defined as the ratio between volume of water to the total volume of voids. We can present it as a ratio or we can present it as percentage. Remember that when soil is saturated, it means that all voids are filled with water, and then the degree of saturation is 1, or if we change it to percentage, it's going to be 100%. When we talk about the mass ratios, density is probably one of the most important parameters of soil. There are different adjectives that we use to describe density, such as bulk, total, wet, or even moist, which actually mean the same thing. Density is the ratio between the mass of soil and the volume of soil. When soil is saturated, we also have a water component here. When we deal with dry soil, in this case, we can talk about dry density. And you will see that in this formula, we have only the mass of solids divided again by the total volume of soil. We have a special case when the degree of saturation is 100%, the soil is saturated, and then we can call it a saturation density. Another important concept that we use in soil mechanics is a unit weight, or unit weight of soil. A unit weight of soil is defined as the ratio between the weight of soil that we measure in kilonewtons to the total volume of soil, which we measure in cubic meters. And the unit weight is actually more commonly used in soil mechanics than the density. You will see later that we use a unit weight to calculate the stresses acting in the soil mass. To convert the unit weight to density, we will use this equation. If we know the density of soil, we will multiply it by the gravitational acceleration, which we assume is 9.81 meters per square seconds. And then we're going to obtain the unit weight in kilonewtons per cubic meters. To give you some examples of typical unit weights, you will see that for gravel and sand, unit weight of saturated soil will be in the range from 18 to around 20. It will be a little bit less for silt and clay. Also, if you look at the dry unit weight, you will notice that dry unit weight is always lower than the saturated unit weight. It's because for this saturated unit weight, we also consider the weight of water. In this case, we only consider the weight of solids. That's why it's always low. Moisture content, or what we call water content, it's also a very important parameter that we use to describe soil in situ, and it shows how much water is in the soil. In this case, we're going to use the mass of water, and we will divide it by the mass of solids. And very common, we use percentage, so we will multiply it by 100% to get the water content of soil. You will see that water content can be actually very high. For most of soils in nature, water content will be from about 20 to 30-40%. But for very expensive soil, very reactive soils like, for example, bentonite, water content can actually exceed 100%, and it can be up to 400%, as you see here. Specific gravity of solids, it's another important parameter that we use very commonly to calculate different variables of soil, such as water content, density, and things like that. The specific gravity indicates how heavy the solids are compared to water, and you can see it in this formula. We use the density of solids and divide by the density of water. For most of cases, we will assume that the density of water is equal to 1 megagrams divided by cubic meters. For density of solids, we don't really know exactly the value. We can also obtain it through laboratory test. In this case, we need to know the mass of solids and divide by the volume of solids. Please note that in this case, we use the volume of solids. We don't use the volume of soil. This is a very common mistake among students. Mass of solids is the same thing as a mass of dry soil. So if we look at the density of solids, it is always higher than the mass of dry soil. And the density of solids will be in the range of about 2.5-2.8 grams per cubic centimeters. So in this case, you will notice that specific gravity has no units, and it typically varies in a very narrow range from 2.6 to 0.8, and these values depend on the type of soil, and in particular, it depends on the soil mineralogy.